Hi, in this video we are going to talk about greatest common divisor problem. We are given two numbers a and b. We need to find out the largest number that divides both numbers a and b. For example, if you see a as 4 and b as 6, there are two numbers that divide both of them. One is 1 and the other one is 2. And the largest of these two is 2. So our output is 2. Let's see this example. A is 100 and b is 200. There are many numbers that divide both of them. 2 divides both of them, 5 divides both of them, 10 divides both of them. But the largest number that divides both of them is 100. So this is an example where one number divides itself the other number. So in those cases, the output is the number that divides the other bigger number. So 100 is dividing 200, so our output is 100. Other examples can be 15 and 30. So 15 divides 30, right? Or 15 and 45. 15 divides 45, so our output is 15. Let us see this example. In this example, there is only one common divisor and that divisor is 1. So our output is 1 in this case. Please note that if two numbers do not have any common divisor except 1, then these two numbers need not to be prime. For example, two numbers 9 and 10, they do not have any common divisor except 1, right? But they both are not prime, they both are composite numbers. There is one interesting relation of this GCD with this tiling problem. So if you have two numbers a cross b, and if you make a rectangle of size a cross b, then your GCD problem is finding sides of the largest square using which you can tile the whole rectangle. So you have in this example a 4 cross 6 rectangle. Your A is 4 and B is 6. The largest tile, right, largest square tile that can fill the whole rectangle is of size 2 cross 2, right? So that's why our output is 2. Please note that we can fill the rectangle using 1 cross 1 tiles also, right? But there is a larger size tile 2 cross 2 which can fill the whole rectangle. But there is no tile larger than 2 cross 2 which can fill the whole rectangle. So that's why our output is 2. So there is a good relation between this puzzle and GCD. Now please pause this video and try to write down a function that takes two numbers a and b as arguments and returns greatest common divisor of these two numbers. Let us first talk about a naive solution to solve the problem. The idea is simple. We know that the greatest common divisor can be maximum as minimum of two numbers. For example, if a is 100 and b is 200, the greatest common divisor is 100. It cannot go beyond 100. So we initialize our result as minimum of two numbers, right? In case of 10 and 15, we initialize result as 10. Then we check if 10 divides both a and b. If it divides both a and b, then we return 10 as a result. In this case, it does not divide both a and b. So we try the next smaller number 9. 9 does not divide both of them. Then we try the next smaller number 8, then 7, then 6, then 5. At 5, we see that it divides both of them, right? So our loop breaks at 5 and we return 5. Even if your GCD is 1, what will happen? You will go inside this loop for 1 as well, right? So you will break for 1 as well and you will return 1 inside in this program. So the idea is simple. Start with minimum of two numbers. Keep trying smaller numbers. As soon as you find a number that is dividing both of them, that's your largest number, right? Because we are trying the largest possible number, then we are going one by one lower numbers. Let us now talk about time complexity of this solution. So if you are given two numbers a and b, we begin with minimum of a and b. And in the worst case, we'll never find a divisor until we reach 1. So we begin with the smaller of two numbers and then we reach 1. So our time taken in the worst case is going to be proportional to minimum of two numbers a and b. For example, if your a is 7 and b is 13, so you'll begin with 7, then 6, then 5, then 4, then 3, then 2, then 1. You will stop at 1. So you're taking time proportional to 7, right? So in the worst case, it's going to be minimum of a and b. In other cases, it might take less time, right? It might stop at the first iteration itself. For example, 100 and 200. So we use bigger notation and we say time complexity is minimum of a and b. Now please pause this video and try to think of any solution which can find GCD in better time complexity. There is a standard algorithm called Euclid algorithm. We are going to talk about this algorithm now. Let us first get basic idea behind Euclidean algorithm. The algorithm is based on this claim that if b is smaller than our other input number a, then GCD of AB can be written as GCD of A minus B comma B. Let's now see how is this claim true. Let G be the GCD of two numbers A and B, which means we can write A as Gx and B as Gy, where x and y are integers. And since G is the GCD, there should not be any more common factor between x and y. So GCD of x and y should be 1. So we can write A minus B as G common x minus y. Now we need to show that B and A minus B also have GCD as G. How do we show it? See, one thing is very clear, G is a common divisor. We have written B as Gy and A minus B as G comma x minus y. Now how do we show that G is the greatest common divisor? See, if there is a larger common divisor, then there should be one more common factor between x and y. And this contradicts this, right? So G has to be GCD of A minus B and B also. Here is implementation of Euclid algorithm using the basic idea that we just discussed. So while A is not equal to B, if A is greater than B, then do A equal to A minus B. Otherwise, B is greater than A. In that case, do B equal to B minus A. And stop when A and B become equal. In that case, you can return any of the numbers A and B as your final result. So here is a dry run. Say if A is 12 and B is 15, you are going to do B minus A, right? Because B is greater and they are not equal. So B is going to become 3. Then you are going to do A minus B because now A is greater. So you are going to get 9 and 3. Then you are again going to do A minus B. So you are going to get 6, 3. Then you are again going to do A minus B. And now you get 3, 3. Now they become equal. So you stop your loop here and then you return 3. This is basic version of Euclidean algorithm. And instead of doing repeated subtraction here, we can do modular division. We are now going to talk about an optimized version of Euclidean algorithm. Here is optimized implementation of Euclidean algorithm. So we have two numbers A and B. And if B is 0, then we return A. Otherwise, we return GCD of B comma A modulo division B. So if you take a closer look at this, we are not doing repeated subtractions. We are using remainder after division. And if we notice the parameters, we can notice that in all the recursive calls, this parameter is going to be greater than this parameter. Because what is this parameter? This is remainder after you divide A with B. And remainder when you divide by B is always going to be smaller than B, right? So this parameter is going to be smaller than this parameter. But in your initial call, if you pass the second parameter which is greater, right, then the first recursive call is simply going to swap these two parameters. Let's see with this example. If I pass 12 and 15, then in the call what I am going to pass? I am going to pass 15 here and I am going to pass 12 modulo 15 here, which is going to be 12. See, if I do x modulo y and x is smaller than y, then my result is always going to be x, right? So in the first call, it's simply going to swap the two numbers if the first number is smaller. And in all the subsequent calls, this number is always going to be greater. Here it is greater, here it is greater, here it is greater. Why? Because in the recursive calls, we pass B here and we pass remainder after division with B here. So first call makes 15, 12. The second call is 12 here and remainder when you divide 15 by 12, which is 3. In this recursive call, you have 3 here, right? B goes this side and remainder goes this side. And this side we'll have 12 modulo 3, which is 0. So we get the remainder as 0. So we make a recursive call for this. And when you make a recursive call for this, this is simply going to return 3 to its parent call, because when B is 0, you simply return A. And this code is so elegant, we don't even need to check if A is greater than B or B is greater than A, or whether A becomes 0 or B becomes 0. We know that B is going to become 0 first. So this returns 3 here. Then this call is also going to return 3 to its parent call, and this is also going to return 3. Right? So finally we get the GCD as 3. Here is one more example try run. Let's say we have numbers as 10 and 15. So in the first recursive call, we are going to pass 15 here and 10 mod 15, which is 10 here. So it's simply going to swap these two numbers. Now what are we going to do? We are going to pass 10 here and 15 mod 10, 5 here. Now we are going to pass 5 here, 10 mod 5, 0 here. So when we get 0, we return 5 to the parent call. So we get 5 here, then this returns 5 to the parent call, then this returns 5 to the parent call. So finally we get the GCD as 5.